Welcome you all to the 15th lecture in the lecture series on nonlinear dynamics. So I'm very happy to introduce you today's speaker, Dr. Shashi Srivastava from Variable Energy Cyclotron Center, Kolkata. I will read out his biodata in a very brief manner in view of MSc students. So he did his PhD in Homi Bhabha National Institute, India, and he continued his postdoctoral studies in Max Planck Institute for Complex Systems, Dresden, Germany, which is a very famous institute for nonlinear dynamics people. And I think he joined as a scientific officer in the Variable Energy Cyclotron Center, and he is serving at the Variable Energy Cyclotron Center from 2018. And as far as his academic works are concerned, he works in several topics in nonlinear dynamics, including random matrix theory, entanglement, content and generation, and quantum dynamics of systems out of EPDM. And as far as his industrial work is concerned, he worked for a couple of projects related with high intensity accelerators and rare ion beam facility developments. And he has published several articles. And one notable thing is he is an outstanding reviewer for Journal of Physics here of the year 2019. In fact, I came across the opportunity to hear his talks in a couple of places. And he's a very good speaker. So that's why I have invited to give a talk in this forum. In fact, he has given talks even outside India, including Germany, UK, and all are well cited. So with this short introduction, now I invite Dr. Srivastava to deliver his lecture. Over to you, Professor.
Thank you. Thank you, Professor Senthil-Velen, for such a nice introduction. And let me from the very t equal to 0 kind of make it very clear that I must apologize to all the experts who are out there in the audience that today I have prepared my talk in such a way that my target audience is the students. So I will be doing mostly board work, and in that process I will not assume I will assume practically nothing. So all the students are very welcome to ask questions if anything is not clear. Okay, and right at the point when it occurs, not you should not wait like at the end of the talk to ask a question. Is there? So I see a raised hand.
Yes. I don't know why she has by mistakenly. Rajakumari, do you have what you want to raise? No, I think by mistaken.
Oh,
yes.
Okay. Okay. So let us start today's talk. But before that, let me share my board with all of you. So
No.
Can everyone see this?
Yes, it's coming up.
Like the whiteboard, yeah.
Yes.
Okay.
Yes.
Okay, great. So what I am going to talk about today is, as the title says. Okay, let me choose a different color pen so at least everything is visible. Okay, so the relaxation dynamics of multiply quenched harmonic oscillator. And the choice of the subject has two purposes mostly. First, that we all are kind of have started our journey in quantum mechanics and in any other classical physics as well with harmonic oscillators. So this is like one of the most familiar system that we know of. And this happened to be also like a prototype example of any integrable model that you can think of. And still, it has interesting things kind of hidden that if we try to explore, we can learn a great deal about how a system, if we put it out of equilibrium, then how does it behave and what are the properties. And in today's talk, I will be mostly kind of interested in the entanglement between two subsystems. Okay, and individual subsystems are bunch of harmonic oscillators. So it's as simple as that. Okay, and I would also be interested in some of the things like momentum distribution, and and I am pretty sure that by that time I will exhaust all my time, and therefore I won't be able to go in the something called a modern quantifier in some sense called out of time order correlator. But that's also you can study using such a simple system and can get a very nice insight in non-equilibrium dynamics of quantum systems. Okay. So let me kind of start with so before I say something more, let me also say a few things that these studies are not only like purely from the theoretical perspective, but one can draw motivation from the experiments which are used with like cold atom experiments, and where people have tried to follow. I mean, now it's very nice to kind of do experiments in which you can follow complete unitary dynamics of a quantum system, and therefore one can understand a great deal of the intricacies of such dynamics. I will be quoting only two experiments because that's, I think, it gives you the perspective that what to expect from a typical system and what to expect if the system is kind of integrable. So let me choose the first experiment, which was done by Kinoshita, Wenger, and Weiss back in 2006. And let me show you a picture which kind of gives a very nice summary of the whole work. And I hope that everyone can see this picture. So this is from the work of Kinoshita et al. Right, back in 2006. This work was it appeared in Nature. So what was done is they choose basically a few hundred atoms of rubidium, which is a classic example of Bose systems. And they started, so basically there was a trap in which you can kind of keep two bunch of rubidium atoms in two sides and give a momentum which are opposite to each other. Okay, so what would happen, that suppose this is the trap in which they are trapped, and suppose now you kind of lower this potential, which means suppose I can delete this in such a fashion, then this will start moving in this direction and this one will start moving in this direction. Now what we expect in general, that if there is two bunch of particles and they are like set free, and then they will start and then there will be collisions, and now because of the collisions there will be exchange of energy, and over some time what you will find that there is a homogenization of energy, and you should not see like their identities preserved. But what happened in the contrast is the picture that I have put here. So if you see, this is what time t equal to 0, and time is flowing in, time is flowing in this direction. Okay. And so the potential has been lowered, and then they start mixing. There's a perfect kind of collision, and then they again go back, and you can see nice oscillatory behavior going on till a very long time. Okay, which means and these are like in a limit when kinetic energy of individual individual systems or subsystem is greater than the energy per atom, let's say. Okay, what it means in nutshell that this was an example of an integrable system, and this was the dynamics that they observed. So it kind of retains the memory, and that is the key message that I want to give you from this picture, that if you have an integrable system, and if you allow them to even mix for a very, very long time, it retains its memory of initial condition. Okay, so that was the one experiment which I have shown you. And there was another experiment, just to contrast this. Let me show you that. So what this experiment I am quoting is by Trotsky and et al. And this appeared in 2012. Again, this was related with one-dimensional Bose gas. But here, the limit was chosen the opposite limit, in which if you write down the Bose-Hubbard model, then you will have the interaction energy per site, I mean at individual site, and that is a dominant term, right? And because of that, the system is a typical system, which you can say. And what they took is they prepared their initial state in such a fashion that that if you kind of say that this is my wells, then they put the atoms in alternating wells. Okay, so this is how they start. So this was the initial state of their system. And after a long duration, what they measured is again that how does this the position of this thing looks like. And what they observed is that, so initially you see at the, if I say that the first side there was atom, then the third side, then the fifth side. So that means at odd side there is a density. But what after like time evolution, they found that the density is uniformized, right? So contrast this with this. Here they were retaining their individual character, but in this case, they found that there is a nice mixing going on, and so to say, a steady state behavior they observe in the system. Okay, and let me kind of show you the picture that that captures this very nicely. And this is the picture that they have shown in their paper. So this is the odd site density. Actually, in their convention, they put it at the even sites. So here it is odd site. And if you see that it starts from 0 and it goes on and kind of follows this and become like at half. So if you think of this kind of thing, so since you have populated here, but it was empty, it was populated here and the other one was empty. So if you take the average, it should be 0.5, right? And that is what after some time. So if you at t equal to 0, there was 0 density, then after some time, this is how the half density, it kind of settles. So like after some time, you will find that everything is filled. Okay. And this was the dynamics that they kind of showed. So, and this was the interaction energy at the site that was responsible for this. And this one can even experimentally, they figured out that when they increase this number, okay, then the picture changes something like this, that you can see the oscillation even here, right? There was oscillation, but if you ramp up this U by G, then this thing pretty fast kind of, so all the oscillation kind of damped down even at this level itself. So that was a clear signature that this factor was responsible. And so this is the typical system in which you experiment the dynamics, okay? So two things, if you have an integrable, then this is what we should expect. And if it is a typical chaotic system, so to say, then this is what one should expect. Okay, so this was about the density, but as I said that I am more concerned about not the density, but the entanglement. But before that, what is the framework to study such a system, right? Because this was an experiment, I kind of described it. So these experiments are called quantum quench, okay? And let me define it for you. So a very rudimentary definition would be that I start with a quantum state, let's say psi, okay, and I take another Hamiltonian, let's say H, okay. The condition is that this psi is not eigenstate of this H, because if it is, then you know that that dynamics is very trivial dynamics, namely the phases are e to the power, so IH bar del psi del t and H psi t. If psi becomes eigenstate, then you just have the phase. That's all that changes, right? But if it is not, then that is what is called the quench scenario. So that's the quantum quench experiment. And if you want to study the dynamics of this, then what you can do, and this, of course, this Hamiltonian comes with its own set of eigenstate, let's say phi, okay? And since this is all complete and all, so if you want to study the dynamics, the psi you can expand in terms of this phi, right? And it simply means that you can write down the psi as C alpha, phi alpha, okay? Where C alpha is just the overlap with this phi and this psi. And then later on, the complete time evolution of this psi t, that means at any point time t later on, the state you can write down as a basically there will be this e to the power I, e alpha t, and then C alpha, I can take it on this side, and then the phi alpha, okay? Now, it's not in general the state that you are interested in. You will be interested in the observable, right? Just like we were measuring the density in the previous experiment. So now how will the observable, the expectation value of any generic observable will look like? So if you have the psi t and the O and the psi t, then one can immediately see that there will be a double sum, and there will be I, E alpha I minus beta, T, and then of course there is C alpha star, C beta, and then let me just directly write down O alpha beta. Okay, where O alpha beta is basically just the right. So this is how it will look like. Now, imagine a system in which even the Hilbert space dimension is, let's say, just maybe 2 to the power 10, right? So just 10 spin half particle, and then you have to evaluate the sum. Then it is like you have a double sum over each alpha and each beta. And if you just increase your numbers, n is the number of particles, then 2 to the power n is the each of this index. So it basically just the sum grows exponentially fast in to get this expectation value of this O at any point of time t, which is a hard problem to do, right? So what one so if you think about a system which is thermodynamic in the thermodynamic limit, then you would say that this is a hopeless problem and let's not even bother about it. But then you look for the limits that, okay, can we understand the system in some limit? Okay. And one of the easy limit to take is that if you take t going to infinity, okay, then you know that all these phases are going to fluctuate very, very rapidly. And over time, you can average it out. So they will go to 0. And only thing which will survive is alpha equal to beta. That means the diagonal things are the only things which are going to survive, right? And in such a limit, this, if you say O, is going to be given by alpha, and then and this is going to be alpha, right? Now contrast from this situation, here you had n squared term, and here you have only n term. So the simplicity is like exponential simple set, even in this case. And this is exactly what is called diagonal ensemble. Okay. So this is essentially the content of diagonal ensemble, what people talk about in the literature. And it simply means that in the time infinity, a very large time limit, what you can get your expectation value of the typical observable by just focusing on the diagonal part of that system. Okay, but in some cases, if your system is typical system, and that typicality means that it is or a generic, then it means that it has some element of chaos and all that, and because of that, you can go into the actually one can show this, that for all the local observable, you don't even need to have all the n sums to evaluate. This you can replace, this expectation value you can replace by just the Gibbs ensemble. Okay, and this is a very, very great deal of simplification, because then you have only one parameter in this whole system, and that would be like energy of the typical system that you are talking about. So this is about a typical system. But even suppose you are talking about an integrable system, then what happens that you have a number of conserved quantities. That means ij, and this is going to commute with h, and they themselves are in involution. And then the Gibbs ensemble kind of generalizes, again only for the local observable I am talking about. Gibbs ensemble is Gibbs ensemble, or in short form GGE. Okay, and it takes the form simply by e to the power minus beta k ik summed over k. So this rho goes like this. Okay, you are familiar with such a construction in your statistical mechanics course. Actually, the Janes, back I think in 60s or sometime, he introduced this way of getting the density in its statistical mechanics. So, and this betas are nothing but the Lagrange multiplier. Okay, so this is a generalized version of the Gibbs, which is called just the name, generalized Gibbs ensemble. And but this work for only local observable. And in some sense, it is good enough, because that is what you are going to measure in any experiment. Okay. By the way, Marcos Rigol is often given credit for that. Okay. But this is the same construction that James used for deriving the grand canonical, and all other ensembles. Okay, so that is about the thermodynamics part of the dynamics of the system, which you have deliberately put out of equilibrium. But as I said, that our focus in this talk will be on the entanglement. So, what are the possibilities for entanglement that we have, or what we know for the integrable system? So, I mean, for all the chaotic system, there is a great simplification that occurs. Namely, you have the results from random matrix theory. Okay, and this kind of takes care of like how much entanglement you can expect between two subsystems, given that those individual subsystems are chaotic, and you can do a great deal of analytical work in this realm. And some of our work from last couple of years, starting from I think 15, that we have developed in this direction, along with Arul Lakshminarayan from IIT Chennai, IIT Madras Chennai, and Steve Tomsovich and Arne Backer from the Dresden. Okay, but again, today's focus is not this part. Today's focus is the integrability part, where these things are not valid. Okay, so for the integrable cases, the entanglement so one of the most popular theories that is around is by Calabrese and Cardy. Okay, and this theory is more of a phenomenological way of understanding that how much entanglement is available between two subsystems, and what will be the time evolution. I mean, how the entanglement entropy would grow as a function of time. And it also tells you about that if system has certain properties, then what kind of area law or volume law what you should expect. Okay, and each of these terms I will actually quantify in a minute. Okay, so this theory, let me very briefly kind of tell you about. So what this actually talks about is following. Is there some? Okay. So what exactly this talks about is the following: that the moment you have put an initial state under a different Hamiltonian or in the setting of quench, so then the energy of, there is an extra amount of energy is being pumped in the system. This is what happens in the quench. Okay, now, so the phenomenology starts right here, that suppose if you have this system which is denoted by this line, and this is the part of the subsystem, this is the part of the system which you are calling as a subsystem. So a portion of this energy in this subsystem will be used to create certain quasi-particles. Okay, so these are not real particles, these are a phenomenological way of understanding entanglement. So these are quasi-particles that will be created, and the assumption is that these quasi-particles will be entangled. So, so this extra energy, this leads to generation of quasi-particles. Sorry. quasi-particles, okay? And this quasi-particles, if they are at the same space time, then they are entangled, okay? So this is the simple set of assumptions that they choose. Now, and one more thing, and they evolve ballistically. Okay. So now if a particle was created here, it will just follow ballistically like this, right? This one will go like this, like this. So now the way I have drawn, you can see that I have generated just 4 particles, but they are not at the same space. Therefore, at t equal to 0, the entanglement in this subsystem is 0. But at certain point time t, they cross, these trajectories of the quasi-particle cross each other. Now at this time t, there will be some amount of entanglement generated, okay? And then at later time t, this thing crosses the trajectory of this, so there is some more entanglement being generated. So now you can see that the generation of entanglement is going to be proportional to t, because you have chosen such a ballistic motion, okay? And after some time, what will happen? All these trajectories have crossed each other, right? And once they have crossed each other, then there is no more entanglement that can be generated. So after some time, initially, and after some time, there will be saturation, right? And now what value it should saturate? So it will saturate because the entanglement was produced by these trajectories, and trajectories are from this of this quasi-particle, and the number of quasi-particles are decided by the subsystem size. Then the saturation value is going to be proportional to length of the subsystem size. Okay, so these are the very simple set of assumptions, and it creates like he bypassed the total mechanism of creating calculating the reduced density matrix, and from there calculate the von Neumann entropy, etc. He just said that it is like basically a hydrodynamics of quasi-particles. So it becomes a simple problem, but now it depends on certain parameters. What are those parameters? Is basically the group velocity with which it will travel. So parameters is the Vg, the group velocity with which this one travel, and it also depends that how many you have produced, right? So the cross section of the generation of the particles, right? So these are the things which kind of is still unknown, right? So this is why this is a phenomenological model. You have to somehow calculate or have the idea about these two things, and then you can write down that up to certain limit, the entanglement will look like, if you kind of plot as a function of time, then it will just grow first linearly, and then there will be a transition regime, and then it will saturate like this, okay? And this is something like this, or what is the exact function which kind of joins this two is not yet known, okay? But this is a phenomenological model which works. So this is your entropy. Okay, so this is again, as you can see, it's a very simple model, powerful to some extent, but it is approximate. Okay, so now this is where comes our work. That what we plan to do is kind of take a simple system, right? And since it has to be integrable, because that is where our interest is. So simple integrable system, okay, and put it in the quench scenario, okay, and then try to study the entanglement but the demand is that we want it to be exact. Okay, no approximation at any level whatsoever. Okay, so these are the demands that we want. Now, these are kind of the prerequisite of the work. So, okay, then our choice is that let's take the harmonic oscillator. Okay, that's a simple system. We all agree on that. And we will see that, okay, quench protocol. So I am going to, since I am going to directly talk about the multiple quench, so what I am going to do is one of the parameter in harmonic oscillator is certainly the frequency. And this is what I am going to make time dependent. And the dependence that I am going to attribute is like it is at this level for certain time, and then it kind of switches the value from this to this. Then it switches the value again here, switches the value again here. And this is what the number of time it kind of switches this value is that many quench I am talking about. Okay, so this is the number of quench. So in this case, the example, it is 3. Okay, good. So how to calculate the entanglement? And then that means we first have to get somehow the wave function, right? The wave function at arbitrary time t, okay? And then from there, we have to calculate, we have to define that what is our system and what is our subsystem, system and subsystem, right? And then trace over the system part and get the reduced density matrix of the subsystem. Okay. And once you have the reduced density matrix of the subsystem, then the entropy is just defined by minus rho log rho. Okay. So that is what we are interested in calculating. But our demand is that everything has to be exact. Okay. Thankfully, that this system, the choice of the system allows that. Okay. So what we are going to talk about, that I have kind of introduced the subject, that what the quantum quench is, how people are calculating in general scenario of two kind of dynamical system like chaotic and integrable, that what is the scene right now in the chaotic situation and what is the understanding in the integrable models, and what we want to do, what we aspire to do in this study. And then now in the rest of the talk, what I am going to do is that I am going to illustrate kind of everything that that you need to do to reach at this stage. Okay. So again, as I said, that I am not going to kind of assume anything. So all these calculation we will try to do as much as possible here itself. Okay. Good. So before I go to like multiple harmonic oscillator, let me demonstrate you that how for such one harmonic oscillator we can solve this problem exactly. And I think at least in Bharatidasan University, since there's a rich legacy of nonlinear dynamics, most of the things that I'm going to do will be known to you. But still, I am just going to very quickly kind of repeat it. Huh? Okay. And let me kind of request Professor Senthilvelan that please let me know about like 15 minutes is left around that time, so that I can stop and take questions from then on.
You can go 45 minutes more.
Yeah, thanks. Yeah. Okay, so if I have a time-dependent harmonic oscillator, then p squared over twice m plus m omega squared t by 2 x squared. Most of the time I will choose m as 1, h bar as 1. So if you don't see anywhere h bar or m, just assume that they have been set 1, and I will I mean, kind of switch between them. So just take care of that one. Okay, so this this method of calculating or solving this problem is goes back to the work of Armakov. Okay, and then it has been contributions has come from Milne, then Pinney, and then many more. Okay, and somehow this is the method of invariant that I am going to discuss right now. So if you are coming from classical physics, especially accelerators, then the same invariant is also known as Courant Snyder invariant. Sometimes it is called just the Lewis invariant. Okay, so various name depending on which community you are coming from. Okay, but the work is like from Armakov in the very beginning. Okay, so here what I am going to do is directly jump into the quantum domain. So the idea is that if we can find out a time dependent invariant, okay, and which is quadratic in x and p, then we can solve the problem exactly. So let us think about it that, okay, if I of t is that invariant, and I am, it has to be quadratic in p and x. So the only possibility that one can come up with is this. Okay. And you must notice that I have put xp plus px because I am already thinking quantum mechanically. Okay, and therefore I don't want to write 2 times x times p. Okay, and what is the definition of time? The invariant that this di dt must be equal to 0. Okay, or in this settings, this will be del I del t plus 1 over h bar I h. This has to be 0. Okay, so now all you need to do is just put this I, this because this is an unsatz and there is alpha, beta, gamma still unknown to us. Just put it here and try to find the constraint which you will need to have the answer. And this I'm just going to write. So I am going to basically write down all the steps that is kind of important, but in between there will be like just one differentiation or one equating to 0. Those are the kind of steps that I am missing. Okay. And now you can see that these alpha, beta, and gamma, all the differential equation first order, but they are coupled, right? And just to kind of have some sort of simplicity, let me introduce another variable, which is like beta t. I am going to talk about as rho squared t. I will come back and tell you that what is the significance of this alpha, beta, gamma, or maybe I can just tell you right away that at the end of this, you will see that is this beta is like amplitude of the oscillator, which is time dependent. And this alpha, this gamma is actually the phase factor, and the alpha is a time dependent constant, which comes out here. And therefore, this is like you have some sort of envelope going on, which is oscillating. And this is the key thing in accelerators, which people use in high intensity accelerators. And this function, because it was denoted by beta, is kind of known as beta function of the accelerator. So that is just a side remark for the people who are interested in a bit of accelerators. Okay, so now if I put this kind of substitution, then you can write down all this 3 in terms of the rho. Okay, and this leads to an equation which is called rho double dot plus omega squared rho is, okay, this is the cube. Okay, and And this is the equation which is called harmonic equation. Okay. Fine. So if we solve this equation, then from solution of rho, one can get beta. And if you put all these things, then you will get all the alpha and gamma also in terms of this rho. So everything will be known. So once you solve just this one equation, okay. And finally, my invariant, this I can be written down as m squared. So this is my my invariant, Lewis invariant, Courant-Snyder, or whatever name you choose. But this is the time-dependent invariant that you can find out for a harmonic oscillator system. And notice that this invariant is in itself a Hermitian operator. Okay, and therefore you can diagonalize it. Okay, you can write down, even though it is time dependent. So what you can do, you can find out the eigenvalues and eigenfunction instantaneously. At each point of time t, it will have its one set of eigenfunctions and eigenvalues. Okay, so that's what is possible to do, and how to do that is kind of, whenever you see that there is something like quadratic in x and p, and at the end of the day it is harmonic oscillator, so you know that you can write down in terms of the creation annihilation operator. And here this a, the annihilation operator is okay, so there will be something which is proportional to x plus I, and p times rho minus x. Okay, let me write down the whole thing. Yeah. So this is your annihilation operator, and correspondingly you can write down the A dagger, and you can very easily check that A dagger satisfies the usual commutation relation that it does for the time independent harmonic oscillator. Okay, and I is therefore you can write down in terms of A dagger A plus half. Okay, and so that's like number operator plus half, and therefore you know that if any Hamiltonian has the simple form, then the eigenvalues are just n plus half times h bar, the quantity omega. Okay, and you can also, by defining the ground state as A, ground state is the state on which if annihilation operator acts, then it annihilates that, right? So then the ground state phi 0, let me denote that, is simply written as some normalization constant minus n. Okay, so this is a Gaussian, but the standard deviation, so to say, is now explicitly time dependent because the rho is time dependent, right? And this is what the ground state looks like. And once you have the ground state, then in fact you can apply the A dagger and you can find out all the excited state as well, right? So there's absolutely no problem. And now let us, so this was a ground state corresponding to this invariant operator I, right? What about the harmonic oscillator? Because we were after harmonic oscillator from the very beginning, right? So for that, we know that it is going to be, since it is time dependent, it is going to satisfy the time dependent harmonic, I mean the Schrodinger equation, right? Okay. And if it is so, and then we know that H commutes with I. Sorry, I is the time invariant for the corresponding to this H. Then one can basically in a matter of few lines, one can show that this psi lambda kt is like I sum kappa, which is time dependent, divided by h bar square phi xt. Okay, this is a solution of this, and suppose you don't see it directly, that how does it work and how, I mean, so you can just plug this thing here, and then you will get an equation for this kappa. So that will be d kappa dt, and this will be fixed by phi. So this is one equation which you solve, then you can find out this. And turns out that at least for this system, it is quite easy to solve and has the solution, which is okay. So this is the kappa. So you just put it here, and then you have the solution, a one-wave function, which will satisfy your time-dependent Schrodinger equation for the time-dependent harmonic oscillator. Okay, and this part that I have discussed is very well described in there's a paper by Reisenfeld, so it is there. All these details you can find out here. But what I am going to make use of is following, that any psi xt. So this is what I have essentially solved, because psi xt is e to the power minus I kappa t. Phi xt, phi is I have solved here. So this is the solution of the time-dependent harmonic oscillator. So that is like one part of what we wanted to do. And this in general can be written down as following. I mean, all you need to do is just put it here. That's all. So, from the next notation, oh, by the way, let me just tell you that since I want to keep my notations very close to the paper that I have mentioned in the abstract, so I will just switch from rho to B. So rho to B, this point onwards, okay? So I am B dot T over twice BT, okay, minus I. Okay, now this En is like for the general, if you take nth eigenfunction, then this n is needed, but otherwise you can just put En as, like you can put n as 0, and then it is just half h bar omega, okay? And that would be corresponding to the ground state in some sense, okay? I'm a bit hesitant to call it ground state, but that's what it is in the usual definition of ground state. Okay, fine. So now I have a solution for a time-dependent harmonic oscillator, but that in itself is not my interest. My interest is multiple harmonic oscillators that are coupled to each other, right? So if you want to have like coupled things, then let me just show you for the two that how we can write it in a very nice manner, and then from there writing for n is our next step. So for two particles, or let me write down three particles, because two particles becomes too simple. So for the three particles, I mean, what it will be? It will be P1 square plus P2 square plus P3 square, right? So that is one part. The second part is the omega square T, and this will come with x1 square, x2 square plus x3 square. Note I have put the frequencies, all the frequencies same. It is not the most general model, but it is the sufficiently general model. Okay, and then I want it to be coupled harmonic oscillator, so I have to have some coupling term, right? So KT, and I am going to have just the nearest neighbor. So x1 would be interacting with x2, So this is my harmonic oscillator. I mean, 3 harmonic oscillators which are interacting or kind of coupled, let's say, not interacting, but coupled. And now this can be very nicely written as, so for the moment, let me just put the kinetic energy form as it is. And think x1, x2, x3 as vectors. So this is a column vector which constitute like position of individual harmonic oscillator. And then there is coupling, some kind of thing. And then this is x1, x2, x3. Okay. Now essentially you can read off from here that what should be. All the omega square should be on the diagonal, right? And x1, x2, there will be cross term, but there will also be x1 square plus x2 square. So k should contribute in the diagonal term as well. Now, if you you can basically just read that this is 2k, all the 3 diagonal. Okay, and this ones will be just minus k minus k. Okay, so this is a nice matrix that you have found, and what we can do is that if you pay a little bit attention, then you see that the next row vector is generated from the first one by just rotating. So omega square plus 2k minus k minus k, I just rotate in this fashion. So next time minus k goes here, omega square plus 2k goes here, minus k goes here, and next time again. So such kind of matrices are called cyclic matrices. Okay, and notice that I have chosen this term and this term as equal, and therefore it is a symmetric matrix. But in general, one can choose like this is some other k1 and k2, and then this will be a symmetric matrix. So cyclic matrices come in different varieties, and they have very nice spectral properties. Okay. And the best thing is that one can solve it analytically exactly. And some of my early works in PhysRev E are related with the cyclic matrices and the symmetric version of this back in 2007. So spectral fluctuation about these cyclic matrices, one can look up there if one is interested. Okay, but the key thing that I am going to use here is that all the cyclic matrices are diagonalized by what is called Fourier matrix. Okay, and okay, before that, you can also think of this as P1, P2, P3 as a vector, right? And you can put identity. Right. So now you have your Hamiltonian. You can write down as Hamiltonian is P transpose identity P plus X transpose this matrix, which I am going to write down as sigma X. Okay. So this is a very simple way of writing now this multiple thing, and now I can generate and generalize it for n by n very immediately, right? Because all I need to do is just in place of this is a 3 component vector, I can make it an n component vector. And one more thing, notice that I have used the periodic boundary condition because x3 and x1 is again coupled. So in that limit only you will get this cyclic behavior. And since I know that all the cyclic matrices are, so any cyclic matrix M is going to be diagonalized by F, like the F dagger, where F is the Fourier matrix, then what I can do is I can use the sigma, the spectral decomposition of the sigma here. And okay, And now let me also do this. FF dagger. And redefine this as a new thing, which is called y. And this you can define as p tilde. Okay. And then this is basically just the diagonal, basically uncoupled form of the harmonic oscillator, right? So this will be p tilde transpose p tilde plus y transpose y. Same Hamiltonian, but now they are uncoupled. And the good thing is, actually there is a, let it write down this way. Hello.
Yes.
Am I audible?
Yeah.
Yeah.
Go
Okay.
ahead. Yeah,
Fine.
go ahead.
Fine. Okay. So now what I achieved here is following that I had started with coupled harmonic oscillator, right? Coupled harmonic oscillator. And I managed it to like uncoupled harmonic oscillator. Okay. And once I have this, then if it is like let's say 2 or 3 or 4 uncoupled harmonic oscillator, then the wave function of individual, the total harmonic oscillators will be just the product because they are uncoupled, right? So I can write down the wave function in this space, and then I can go back here and have the wave function for the coupled harmonic oscillator. So that was the simplification that I kind of have achieved by doing this, right? Is there any confusion at this point in anyone's mind? Because I think this was one of the crucial steps. If you want to find out an exact solution for a coupled problem, then the method that we are going to use is following that we are trying to have an unitary transformation which uncouples this, finding out our solution for single particle problem, write down the wave function for n uncoupled particles. And then since it was the unitary transformation which was going from coupled to uncoupled, I can always go back and then I have solution of the problem which is for the coupled problem or the coupled harmonic oscillators, right? Okay, so if that's like kind of clear to everyone, then let me write down at least for those 3 particles. The psi in the y1 space is just written as e to the power minus I m and then there is this okay. You see, I have just written down as a product. Lambda ones are the eigenvalues of this. So lambda was the general, I mean, I have denoted the diagonal matrix as lambda. So lambda 1, lambda 2 is corresponding to individual harmonic oscillator. And this y I have defined already, this root lambda 1. So this is just the determinant, right? and everything else. And B was this row that I have already kind of told you. So this capital B is the diagonal. So capital B is just diagonal matrix B1, B2, B3, right? So B dot is like B1 dot, B2 dot, B3 dot, and then you can define B dot by 2B because both are diagonal matrices. Similarly, this is B to the power 4. Now this is written in the uncoupled form. So all I need to go is transform back. So I put Y as, you see F dagger X was Y. So in place of Y, I just use that relation and then I can write down in terms of X, which are the coordinates for the coupled harmonic oscillator problem. Okay. One more thing, maybe let me just for the notational purpose that yeah. So this thing which I am so in uncoupled psi in x1, x2, x3, this becomes essentially determinant of omega over pi 1/4 e to the power minus half x transpose b tilde x minus half. Okay. Sum over I and e to the power minus half x transpose omega x. Where I have denoted this b tilde is nothing but, if you see this equation y, then there will be f. So y was f dagger x, so this will be xf, and then b tilde and then f dagger. So b tilde is defined as f diagonal of b dot over twice b, okay, and the omega is just f, and this is f times root of lambda to the power b4 f dagger. So that is just the notation purpose, and this is like determinant. Okay. Now I have essentially solved for arbitrary time dependent part, and I hope that you kind of realize that so far in all this calculation, if you start from here, I haven't really specified what is the form of t, omega t. So omega t is a general time dependence, right? Till this part. So there was no time dependence. That what form I am choosing and how I should solve, that is not given. Okay. So it is for any arbitrary time dependent problem. And now I am going to kind of kind of adopt this for my own problem, which is like, okay, so first thing that this, in each of this, if you see that the only thing which is unknown is like this b's, right? Even here I know, if I know b, then I have this factor intact. If I know b, then I have this factor intact, and everything is known. So the only thing that we want to know is what is the solution of the Armakov equation satisfied by each of the b. So bi double dot plus lambda I t bi is lambda I0 divided by bi. Okay, so this is for each harmonic oscillator. This was one of the Armakov equation. If we know the solution of this, then immediately I can write down my wave function. Okay, and this again just by changing my variable from of this form, I can reduce it to an equation which is kind of easier to solve. Okay, and so I am going to write down directly the solution of that. So eta I dot is, okay, since I am going to write directly the eta I. So eta I will be sorry, not alpha that I have used. Okay, and this is this one index I have put. So which means that I am going to solve this equation for a waveform which is of this form. Okay, that means it is constant in the ith interval. So this one basically tells me that the 0 to t to tau, and tau is the duration of this. Okay, so in this, each of these intervals I have one of the solution. Okay, so if I know alpha, beta, gamma in each of this, and this alpha, beta, gamma is not going to change in this, is going to change in a certain fashion, and that I am going to write down next. So, but what is important that this solution of eta is like 3 unknown coefficients. So if we know this alpha, beta, gamma, then we know eta, and therefore we know b, and therefore we know psi, and everything is kind of then onwards is easy to get. So now for the multiple quench and
Sasi,
what yes.
where comes this relation eta I equal to bi square?
Eta I equal to bi square?
Yeah,
where
it comes from?
I had just, yeah, so no, so this is I am going to write because in terms of eta, the solutions are quite easy to get.
Okay.
So I am just basically redefining this equation in terms of eta.
I see. Okay. Okay.
Yeah, but if I mean this is one, this is kind of, if you put this substitution, then the resulting differential equation is actually Pinney equation.
Okay. Yeah.
And for Pinney, one can write down the solution immediately, directly. Yeah. So that was the motivation of going through this system. Okay, so then this eta, I am going to define this eta as, so basically let me again, I can do maths in any time that I want, but two things that we must focus, that whenever we are going to change this waveform from here to here, my wave function is going to be continuous, and therefore and the derivative of wave function is also going to be continuous. So these are the physical demand that I want in my system, and which will impose the demand that in turn psi was in terms of b and b was in terms of eta, right? So eta must follow those things. That eta should also be at this point, it should be continuous, and therefore there will be some relation between them, and that is what I am going to derive. So each of the eta, I can prepare a vector eta, let's say eta jt, eta j dot, because I have to make sure that the continuity of eta j dot as well, and eta j double dot. This is an auxiliary equation which I am going to write for a computational purpose. You will see in a minute. Now, okay, just do this. This on this side, I can have alpha, beta, gamma, right? This is J1, J2, oh sorry, J1, everything is 1. Is this part clear? And here, the first row is just going to be cosine, sine, and 0, right? Second one is going to be minus sine, cosine, and 0. So this is cosine 2 root lambda I t, sine 2 root lambda I t, and 1. So eta j is this times this, and 1 times this. The next one is just root lambda would come out, sine. This 2 root lambda will come out cosine, and this is 0. And the third one is just taking another derivative. So this time root lambda and root lambda will become lambda and cos. This is lambda and sine. This is again 0. So I have just going to use this auxiliary equation to have a matrix method, which I will employ for as many quenches as I can do. I mean, as I want, I can use this matrix method to calculate everything, right? Right. So
you have 15 minutes.
Yes. Yeah, sure. So now I for each of the, so solving for eta means solving for alpha, beta, and gamma. So if I can track my alpha, beta, gamma across the quenches, then I have about all the results. And this I am not. So this is actually a pretty straightforward method. That if you go from one quench to the other, this alphas are related. Alpha, beta, gamma is related with this. Okay, and this is now alpha, beta, and gamma. This is Ji, Ji. A I have defined, and B is just coming from the continuity equation, and that will be given as 1, 0, 0, 0, 1, 0, and this will be 2 times lambda jt minus lambda jt plus, and then 0, and then. So this is a matrix which comes just from the continuity, that's all. Okay, so that means I can now have after each quench, I can have my psi function, the wave function, exact wave function. Now the next thing that we need to calculate the entanglement is just the reduced density matrix, right, at each instant. And for that, first of all, we need rho, the density matrix, which will be what? X prime t will be psi star, right? One will be coming with x, the other one will come with x prime. Okay, I have my psi exactly written here, so I can just plug it in this form, and this will take, and now equations will become earlier than the earlier ones, but let me write down this, and after that I will just show some pictures. Oops, sorry. Okay. That this is just a Gaussian integral written in a fashion that each of these coefficients are basically the matrix. But what you can always do, you can integrate some of the degree of freedom in which you are not interested. Okay, and after that, now let me kind of write down the expressions directly from the paper. So if I am interested in the reduced density matrix of the single oscillator, right? Remember that my oscillators were using this periodic boundary condition. So I had this oscillator sitting here, 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 and here. So if I say that I am interested in the reduced density matrix of a single oscillator, it doesn't matter which one, because of the periodic boundary condition, this one is kind of ambiguous. So for a single oscillator, my reduced density matrix takes this form. Okay. This comes, so there, let's just kind of try to understand that what it is. So there is this gamma z and gamma minus beta. Okay, this is a phase factor. So this gives you, like, in your reduced density matrix, there will be some diagonal component, right, and some off diagonal component. So off diagonal component means that x prime is different from x, and diagonal component means x is equal to x prime. So now if you put x equal to x prime, then this phase factor kind of goes away, right? So you have only this part. And if you say x not equal to x prime, then this is what these coherences are, right? So in any density matrix, you have the two information. One is like about the coherence of the system, and the other is purely the classical probabilities which you can think about, right? So if a density matrix becomes diagonal density matrix, right, which means that it has become completely classical, or in other words, it has become totally thermalized. Okay, so this is one of the thing which people have, I mean, in most of the usual system, it is very difficult to show that whether it is going to be a diagonal matrix in T infinity limit or not. And now what in the next picture I am kind of going to show is that two things. First is, let me directly write down this. If you see that I have defined a ratio, which is ratio of the reduced density matrix xi and xi plus delta. That means it is the off diagonal part. And this is xi and xit, which means the diagonal. So this is off diagonal versus diagonal. And it depends on this factor gamma minus beta and minus gamma, right? So if the time, in the time this gamma minus beta goes like, I mean, if it suppresses, then this is going to be suppressed exponentially fast, right? And it is going to be a diagonal matrix pretty fast. So all it depends now to, I mean, all it needs to show is that how gamma minus beta is going to change. And gamma minus beta, if you see, it is, okay, let me show you two things. So if I have just a single quench and my number of oscillator is 20 and 500, then you see that gamma minus beta is still much more than 0, right? And gamma is still substantial. So what is going to happen is this reduced density matrix is going to be diagonal pretty fast. Okay, so that already shows that it is going to, and second thing, that the time independence kind of vanishes. You can see that as n is 500, it has almost a constant value, right? So that is going to be a steady state. So one, steady state, and second, it is going to be a diagonal matrix. So these are the two things, but this is still just a single quench. So where the role of multiple quench comes, if you kind of see now that how the multiple quench behave, gamma minus beta pretty fast is going to 0, but then this gamma is saturating at a very high value, right? And in the reduced density expression, there was exponential minus gamma, so it is going to go very, very fast to a diagonal. So the bottom line is that thermodynamic limit, that is n is large, and T large means even 200, steady state and diagonal density matrix. Okay, so that's one conclusion. And now, as I promised that I will be interested in the entropy. So the entropy, okay, let me just show you first the momentum distribution and then entropy. Okay, so this momentum distribution, you can just take the Fourier transform of that, and then you will get the momentum distribution, and you can see that it very, very fast, as a number of quench, it settles to one value, right? So contrast it with your integrable experiment that we kind of saw it here. In this case, it was maintaining its initial characteristic for very, very long time. And only in the chaotic system, it was being homogenized. Here, this is an integrable system, but because of the quench, it goes to the limit which we found for the chaotic systems, right? So this is one of the thing. And second, let me now show the entropy. So this is the entropy result. And you can see that, first of all, that entropy grows pretty fast. I mean, on the time scale, it's just maybe 10 or 15, and it attains its maximum value, and then onwards it is constant. Okay, and similarly here. Now, if you kind of think about the Calabrese method that we talked about, the quasi-particle method, then the saturation is like given here. But the interesting point is that as you put the number of quenches more and more, the saturation value is going to be different, and that one can argue in the sense of that, as the number of quenches are increasing, since harmonic oscillator has the infinite dimensional Hilbert space available to it, so each of the state after one quench, so let's say that initially my wave function was this, and after one quench, the amount of energy that I have put extra, it kind of accesses this many states among the Hilbert space, right? In the next time of quench, in each of these are going to be accessing lot more states, right? And then in the next quench, again, lot more states. And the more part of the Hilbert space that you cover, that means more entanglement you are producing in your system. And that is why, as a function of number of quenches, you have more entropy, right? And this is what is kind of the result that we wanted to talk about today. So we kind of studied the density, momentum distribution, and the entropy. And in all, one hallmark is that there will always be steady state, right? Which, if you think about the integrable model system experiment to begin with, it is in contrast, right? Because there it was for very, very long time, it was persisting with their memory and all. But here, because of these quenches, multiple quenches, actually, if I had shown the single quench result, this is the single quench result, and you can see that it mimics its memory, right? It always, there are recurrences and all. So it is important that I take both the limit n large and t large. Okay. So then only we will have this steady state and entropy saturation, momentum also kind of mixing in a nice way. So everything comes out correctly.
Sasi,
And
where comes
thank you all.
Sasi,
Yeah.
I have a doubt.
Yes.
Where comes entanglement here?
In this,
Yeah.
how have I calculated entanglement?
Yeah.
Oh, okay. So I have the reduced density matrix now written down explicitly, right? This
Right.
rho reduced,
Uh,
right? So I can calculate now rho reduced log of rho reduced,
right.
because that is my definition of the von Neumann entropy.
Yeah.
And
Right.
that one can do analytically exactly.
Yeah.
And
Right.
that is what I have just plotted. Okay.
Yeah.
So this
Yeah.
is just the plot of the exact result.
Yeah. That I understood. Then entanglement.
Yeah, this was the okay. So entanglement is defined. So suppose if I had a system, like if I had this two systems which are not talking to each other, then this row reduced, right? This
Right.
row reduced corresponding to this. So I can get, so okay, let me go in here a bit slowly. So this is my one system, let's say A, and this is my B. And then the correct description would be A tensor B, right?
Correct.
And the row of A tensor B can be then written as row of A tensor of row of B,
Right.
if it is uncoupled. If it
Yes.
is uncoupled.
Yes.
But if it is coupled, then it cannot be written in this fashion.
Right.
Right?
Right.
Okay. So now this fact reflect in row reduced. So if I take the row reduced, calculate for this system, then this is still a pure, that means it will satisfy row square equals row, right?
Right. Right.
But for this system, this one will not be row square. This will not be. So this is a mixed state,
Yes.
right?
Yes.
And so this row reduced, if I calculate row reduced log row reduced, then for such a thing, because its eigenvalues will be either 1 or 0, so for this entropy will be 0. And for this entropy will be non-zero, because the eigenvalues of such a density matrix will be between 0 and 1,
0.
right? So the fact that I am getting a non-zero entropy means that my this single particle, this picture that I drew, this any of this particle is interacting with rest of the system.
Okay.
Okay, so that is the entanglement part. There is also one nice thing, if you see that, suppose my beta comes out to be 0, right?
Okay.
Then xi and xi prime are like just product of two simple Gaussians.
Yes.
And then there will be no entanglement, right? So entanglement comes because of this presence of beta.
Wait.
Okay.
Okay.
So one can even physically think about that why entanglement comes, and mathematically this is the term which is responsible for that.
Okay.
Okay, then thanks everyone for listening it.
Yeah.
So if you have any question, any comments, then now talk is open for that.
So questions from audience? Yeah. Maybe I will ask them to write. Sometimes they hesitate.
Yeah. In case somebody is interested, then let me write down my email ID. So shashi@vecc.gov.in, and you can always write an email to it.
So is there any questions, students? No, I'm not hearing anything.
Okay. Yeah, I am sure that
thank you.
they have to go through it.
Thank you very much for accepting our invitation and delivering a very elementary lecture. I mean, very beautiful lecture, I can say. I learned a lot about quenching the chain of harmonic oscillators, in fact. Yeah. But have you tried for any other nonlinear system? non-linear unharmonic, I would say unharmonic oscillator.
Yeah, so for enharmonic oscillator, I mean, then one has to, I mean, the moment you go from away from harmonic oscillator, then exact that requirement we can't.
So we have some
enharmonic
exactly
oscillator.
solvable systems, right?
Yeah, so there was, we were thinking about something like, incidentally, that if you have a system, something like x square plus a by x square, right? That also
Yeah, you know,
is analytically solvable.
yes.
Right?
That is also
And
in terms of
exactly, and that kind of that kind of goes through this method. But the only problem is that if you want to couple it linearly, then xi plus xj square, I mean xi minus xj square is there, but this 1 over xi square minus xj square, that becomes an issue.
Yeah. Now I
So there are very handful of system which can actually accept this thing. But that is the only, I mean, this only thing is that if you want to do it exactly, the moment, if you kind of allow, because this method is quite powerful, you have a matrix which kind of allows you to go through all the quenches sequentially. And then that is, I would say that is, I mean, all some systems which are not even exactly solvable, that they are also amenable to such things. So yeah, so we haven't really taken up another example.
Yeah, now I can understand the intricacies.
Yeah. Okay. Thanks.
Thank you, Sasi. I will write to you. Okay.
Yeah, sure.
Regarding other things. Okay.
Yeah.
So
Please.
let me know in detail. Thank you.
Okay. Then. Thanks. Bye.